First 5 weeks, 5 weeks, I'll be doing chemistry. All right, specifically bonding, specifically intramolecular bonding. So what I'm going to first tell you is that there is 2 parts to the bonding topic. The 2 parts to the bonding topic. Boys, focus. All right, headphones out of the ear. Headphones out of the ear. That, yes. Intramolecular bonding. That's what we're doing right now in term 1. In term 3, I'll be doing the other thing, which is intermolecular bonding. I'll very briefly describe intermolecular bonding, but that's more of a, so one's intra and one's inter. So currently we're doing intramolecular bonding. All right. I want everyone to know that there's 3 types of bonding. There's 3 types of intramolecular bonding. The 3 types of intramolecular bonding are metallic bonding. There is metallic bonding. There is ionic bonding. And there is covalent bonding. Those are your 3 types of intermolecular bonding that we'll be referring to. Metallic bonding, ionic bonding, and covalent bonding. And you guys should have done that a little bit in school at least, the bare minimum. All right. Now, metallic bonding produces, believe it or not, metallic substances. There is a difference between bonding and substances. So metallic bonding produces metallic substances. Boys, look in each other's eyes later. Focus right now in my work. All right, metallic substances. All right, next one. Ionic bonding, believe it or not, creates ionic substances. And what does covalent bonding produce? Trick question. There is no such thing as covalent substances. So it produces either one type of thing that covalent bonding produces is covalent molecular substances. It produces covalent molecular substances. Another thing that it forms is covalent network substances. And another thing that it's capable of actually doing is if you have something called a polyatomic ion, if you have a polyatomic ion, it actually produces ionic substances. So there you go. 3 different types of bonding, 4 different types of substances. It all relates to the topic of intramolecular bonding. It all relates to that topic. Week 1. We do metallic substances. Week 2, we do ionic substances. Week 3, we do covalent molecular substances. Week 4, we do covalent network. Week 5, we revise it. Then we do physics. Okay, so that's what we're dealing with right now, different types of bonding and how the different types of bonding creates different types of substances. All right, so today is all about metallic bonding. So this is what we're going to do. In fact, this is what we're going to do for all 4 or 5 of the next lessons. What we're going to do is we're going to look at the bonding at a microscopic level. We're going to look at what the bonding, when I say microscopic, we're going to look at the bonding at the atomic/molecular level. We're going to look at the structure at the atomic/molecular level, and understanding and knowing the bonding at an atomic or molecular level is going to allow us, this will allow us to explain the physical properties. This will allow us to explain the physical properties of that specific substance. So today, I'm going to show you the bonding at an atomic or a molecular level in metallic substances. I'm going to show you the bonding that happens in a metal at an atomic or molecular level. And with that knowledge, we are going to therefore be able to explain the physical properties of metals. Today, we're going to learn how to explain the physical properties of a metal. All right. And you've done it briefly with Rudra last few years. Those that have done the science, you've done it with Rudra and whatnot. We have briefly gone through it. So there is just one definition I need you guys to know, before I carry on. One basic definition I need you to know before I carry on. And that definition is electrostatic attraction. What does electrostatic attraction mean? Anyone got a single definition or explanation of what is electrostatic attraction? We hear the phrase thrown around everywhere, electrostatic attraction between this and this. It's simply attraction between positive and negative. That is what is electrostatic attraction. Attraction between positive and negative. That's all it means. All right. Anyway. So, Adi, can you give me any properties of metals, please? Any property will do. Shiny. All right. Yes. One of the properties of metals are that they are shiny. The technical term for shiny is lustrous, which means shiny. Give me other properties of metals. Dense. I think some metals. Okay, yeah, sure. Give me another one. Conducts electricity. That's a good one. Yes, that's probably a very important one. Electrical conductor. What else? Give me other properties, guys, of metals. Thermal conductor. Good. Give me other properties of metals. High melting point. I agree. They definitely have generally. Mercury is an exception. I don't know if you guys know, mercury is a metal, but it's a liquid at room temperature. So there is an exception. But yeah, generally speaking, high melting point. Any other properties of metals? Yes? Malleable. Good word. For those that don't know what malleable means it can be bent into sheets. Its shape can be changed quite easily. What else? Ductile. What does ductile mean? Can be rolled or drawn into wires. The specific phrase is it can be drawn into wires. That's pretty much all I know. Those are properties of metals. Those are properties of metals. Electrical conductor, thermal conductor, high melting point, malleable, ductile, lustrous. We are now going to learn why those are its properties. We're going to now learn why those are its properties. We're going to understand exactly why it's a good conductor. We're going to understand why it's a thermal conductor. But in order to understand that, what do we need to understand? Bonding at an atomic/molecular level. We need to know what metals look like at a molecular level. All right, so let's start, guys. Let's have a read of this. First, just read the metallic bonding. All right, just give me 1 minute. Anyone need sheets still? Not perfect amount. There should be some spares, hopefully. That's right. Leave it at the back. Have a read just of that first page and I explain it to you. Okay. So, I'll tell you some important phrases on that page. This is a very important phrase. Metal elements have low ionization energies. That means very little energy is required to remove the outermost electrons. All right. Everyone should, from chemistry from the last few years, should know that elements like to be stable. And the way that they're stable is to achieve a full outer shell. Metals like to achieve a full outer, everything likes to achieve a full outer shell to become stable. So something like sodium, guys, sodium has got 2 electrons in its first shell, then 8, then 1. Magnesium has got 2, 8, and 2. Having an incomplete outer shell makes them not stable. So what metals do quite easily is lose these electrons. So what it becomes, guys, it becomes an Na+, it loses an electron, and now it has a positive charge. Same thing with magnesium. It loses these 2 valence electrons. It loses these 2 valence electrons and becomes 2, 8 again. That's how it becomes stable. All right. So what I'm trying to say is metal elements have very low ionization energy. And if you want to write down the definition of ionization energies is energy needed to remove the outermost electron. Energy needed to remove the outermost electron. Energy needed to remove the outermost electrons. Outermost electron. So since they have very low first ionization energies, what that means is these metals very, very readily lose their outermost electrons. Sodium very readily loses that 1. Magnesium very readily loses those 2 electrons in the outside shell. So then what happens, guys, is therefore, if you have pure sodium, it doesn't actually look like just this. Pure sodium doesn't look like this. Pure sodium looks like the ion in the middle. And what do you guys notice is chilling between them, filling up that space, those valence electrons. What I'm trying to say is if you want me to use this as an example, sodium doesn't look like this. Sodium actually, what I'm trying to say is sodium does not look like this. Let's pretend that's a sodium atom. So one sodium atom, another sodium atom, another sodium atom. Sodium actually does not look like this because this is an unstable position to be in. All right, it doesn't look like this. So I'm going to write down not this. Actually, what it looks like is sodium loses its outermost electrons. Boys, you keep talking to each other. Yes, you too, the ones talking to each other. All right. So what they actually do is, I can't speak Asian. All right. I just want you to keep quiet. I don't know if the English is getting through or not. Keep quiet so we don't disrupt the rest. Got it? Yes. All right. Talking behind your hand doesn't help. I can still see the muscles move. All right. All right. Sodium plus, sodium plus, sodium plus, sodium plus, sodium plus. This is what it looks like. It loses those electrons. And where do those electrons go? They chill here. 1, 2, 3, somewhere there. That's what they do. Everyone happy with that? That's where the electrons actually go. They don't. So this is what it exists in. This is the form it exists in. It does not exist in this form. And guys, tell me, what charge does sodium plus have? A plus charge. And what charge do these electrons have? Minus. And do plus and minus attract each other? Ah, that's what metallic bonding is. That's what metallic bonding is. The attraction between these positive things and these negative electrons that are just chilling around. So that's what I've written. In the solid and liquid state, the metal atoms release the outer shell electrons. So they are free to move among the positive lattices. So what I'm trying to say, here's the next thing that you need to understand. This definition you need to know. The electrostatic attraction between the positive. The electrostatic attraction between these two things. The positive ions. These are the positive ions, by the way. Positive, positive, positive ions. These are your positive ions. The electrostatic attraction between the positive ions and the sea of delocalized electrons. Guys, I want you to put another word there. Sea of delocalized valence electrons. For those that don't know, valence means the outermost electrons. So the sea of delocalized valence electrons is what holds them together. And that is what we call metallic bonding. That is the metallic bonding. All right. So, am I claiming that these electrons are attracted to this? All right. So this is attracted to this, vice versa. This is attracted to this and vice versa. This is attracted to this, vice versa, etc., etc. So does that keep the whole thing together? Yes, everyone agreed? There's attraction. This one attracts that, that one attracts this. That keeps the entire thing together. That is metallic bonding, the attraction between them. If the metal look like this, guys, does one neutral object attract another neutral object? No, then there's no reason for the metal to stay together. All right, the reason why a metal is held together is the electrostatic attraction between the positive and the negative right there. Okay, what I just drew, that is the electrostatic attraction between the sodium and or the metal cation and those sea of delocalized valence electrons is what keeps it together. And that's what you'll notice I've written. That is what we call metallic bonding. All right, next important thing that I want to write. Next important thing I want to write says this. We're now going to use this property. We're going to now use this property to explain the different properties. All right. It is a high electrical conductor. That's property number 1. It is a high electrical conductor. What do you need in order to conduct electricity? Do you guys know the 2 things you need to conduct electricity? Make a note of it. Make a note that if you want to be an electrical conductor, you require 2 things. You require charged mobile particles. You require charged mobile particles in order to conduct electricity. All right. That's what you need to conduct electricity, charged mobile particles. Do you guys see anything in this picture that is charged and mobile? Yes, what is it? These electrons, everyone agree? They're free to flow wherever they want. The reason why it's called, what's it called? C. I hope everyone knows why it's C, because it literally like fills and flows the gap between them. So that's why it's got C. Delocalized means they're not localized to the originating atom. This person doesn't say, oh, I like to hang around the Na plus that I came from. Thanks, I don't move around everywhere. That's not how it works. This goes wherever it wants to go. It's not loyal to where it came from. All right. C, delocalized because it's no longer localized to that same spot. Valence because it's what? The outer shell, and electrons because they're electrons. All right. So guys, what exactly allows it to conduct electricity? The C of delocalized valence electrons. And you have to explain to me that it's because those valence electrons are charged and mobile. The charged mobile electrons are C of delocalized valence electrons is what allows it to conduct electricity. All right, I'm going to tell you the main properties that we're going to discuss. That's the main one. Now, guys, are they also good heat conductors? Yes, metals do conduct heat well for the exact same reason, the C of delocalized valence electrons, okay? It's not as important, but I want everyone to know, in order to have good heat conductivity, all you need is mobile particles. In order to have good heat conductivity, you just need mobile particles. They don't have to be charged necessarily. You just need mobile particles. So do we have mobile particles in a metal? Yes, the CO delocalized valence electrons are still mobile particles. It's not as important, that property, so I'm not putting a tick next to it, but it is nonetheless a property. All right. Malleable and ductile. Did we discuss the definition of malleable and ductile? Malleable means bent into sheets, and ductile means you can roll it up into a very thin wire without breaking it or snapping it. Everyone knows that you can get copper and make it really, really thin and it won't just snap. It's pretty good. It will just remain solid still, like not solid, but its integrity will be maintained. Why is it malleable and ductile? What exactly makes it malleable and ductile? I'll explain to you what makes it malleable and ductile. All righty, ready? Let's say I've got a pure sodium metal. Let's hypothetically say that I've got some pure sodium metal. All righty. And guys, let's say I apply a force, and I apply a force this way. Let's say sufficient force is applied to the metal. Guys, if I apply the force, is it very possible that these guys will like move over like such? All right, this will move like such. Yes. All right. Ohm, are these electrons going to be like, oh, this electron, by the way, it used to be, look where this electron used to be. This specific electron used to be attracted to that sodium. Okay. All right. It was attracted to it before. Now that sodium's gone away, is that electron going to chuck a cry? No. Is it going to be like, oh no, I lost the guy that I was bonded to? No, what's it going to do? It's like, oh, well, there's someone else here. I'll just bond to them instead. That makes sense? It couldn't care less. It's not like I even use the term delocalized. They're not attracted to that one particular atom. They can just attract to whoever's nearby. All right, they're loose. All right, not loyal. They're like, whatever, that one went, I'll find another one. Okay, there's a word for that. The word for that is this. Not loose. Loose is not the right word. Metallic bonds are non-directional. That is a very important word. Metallic bonds are non-directional. They're not attracted in a certain direction. All right. The electron in a metallic lattice are delocalized and are not attracted to one particular positive ion. They are not attracted to one particular positive ion. They're just there. They're attracted to anybody around them in any direction. All right. So Ohm, was it a huge issue? Was it a huge issue when I applied a force and slid this layer across? No. These guys are like, oh, well, I'll just bond to someone else instead. We're not localized to any particular cation. So does that mean that we maintain the metallic bonds? Everyone in the class agree we maintain the metallic bonds? The thing doesn't snap. We don't go, oh, shit, we lost the person we used to be next to. Let's break up. No, it's just, well, I'll find someone else. All right. What's the technical terms? The technical term is this. When metals are bent or stretched, layers of positive ions are forced to move relative to one another. I drew that picture. However, no matter where the positive ions are shifted, no matter where those positive ions go, the delocalized electrons are free to move into the region between the ions. You need to know this so well, guys. This entire thing you need to know really, really well. All right, I'll just underline what you need to know very well. Yes, they're malleable and ductile. And what you need to understand really, really well is layers of positive ions are forced when, I have a specific word, when sufficient force applied. When sufficient force is applied, which means they're bent or stretched, layers of positive ions are forced to move relative to one another. All right, however, the delocalized electrons are free to move into the region between the ions, which means that the metallic bonds remain maximized. You don't have to worry that, oh shit, the glue is going to fall apart. The metallic bonds are going to fall apart. It doesn't matter. So whatever I've underlined is the key crux to the answer. The layer of positive ions are forced to move relative to one another. So the delocalized electrons are free to move into the region between those ions. They are free to move into the region between those ions. All right, cool. And why is that, guys? Because metallic bonding is non-directional. All right, those electrons are not loyal to any particular atom. What's at the front? Are we writing, underlining? I'm gonna bet money that no underlining. All right. Now, High luster. You already said that to me, right? Adi, one of you said it. It's shiny. All right. I've got the world's worst reasoning to explain why they're shiny, but it does the job for me. All right. I've got two reasons. All right. Is your desk shiny or not particularly? Not particularly. What if I put water on it? Now it's shiny. All right. So is water like wet? And is C like wet? So what I'm saying is there's a sea of delocalized valence electrons. So that C is what makes it shiny. That makes sense? I'll give you another explanation. For those that didn't get that explanation, I'll explain it to you elsewhere. Everyone knows that C is shiny and wet is shiny, so therefore metals are shiny. All right, here's another way I can explain it. All right. If you have a ball here, how do I explain this? Okay, let's pretend we have something like this and I shoot a projectile at it. If I shoot a projectile at this ball, do you think, guys, a projectile might get embedded in the ball? Sure. But now, what if I have a projectile but this ball is moving? If this ball is moving and you hit the projectile, what do you think is more likely to happen possibly if you hit a moving object? It's more likely to bounce off. Aaron agreed? When something hits a moving object, it's more likely to bounce off. That happens in space. The spacecraft have to enter the Earth at a very specific angle because otherwise, because the Earth's moving, they can just bounce off. So the same thing applies here, guys. What is moving inside this thing? What's continuously moving? Sea of delocalized valence electrons. So what happens when light hits something which is probably moving? What's light more likely to do? Get absorbed or just reflect off? Reflect, it just bounces off. That's why metals are shiny. They literally, it's because of those sea of delocalized valence electrons. What's the exact phrase that you use? The exact phrase is they have a high luster, aka they are shiny, because the interaction between the lights, photons, the interaction between the photons of light and the mobile sea of electrons creates the metallic reflectiveness or shininess. Okay, that's all you have to write down. It's just the interaction between the photons of light and the sea of electrons, and that's what gives it a shiny appearance. All right, what else, guys? This is important, this is important, this is important. What's another very, very, very important property? High melting points. Although there's variation, give me a very important variation, guys. What's an exception to this? E.g. mercury. E.g. mercury is liquid at room temperature. So not all of them are shiny. Mercury is specifically a liquid at room temperature. So yes, that's important. All right, now I'm giving a bit of prelude to what I'm going to be discussing next lesson. Does anyone in the class know which of these is the odd one out? One of these is the odd one out. The answer is the odd one out is covalent molecular substances. Why is it the odd one out? Why is this? What do this, and this have in common? Anyone know what these three things have in common? The three things they have in common is they all exist as a lattice. Lattice, lattice, lattice. And for those that don't know, lattice means like a complex 3D structure, a lot of it. All right, whereas this one here, guys, exists like just simple molecules. We call them discrete molecules. All right, here's another analogy I'll use for this. I'm not sure if you guys know, in the Olympics, Russia's not allowed to compete anymore. Not under the banner of Russia anyway. They're allowed to like compete as individuals. All right, that means now Russia can't be like the winner in the medal tally, okay? So think of Russia think of the individual athletes in Russia as like discrete molecules. They're just individual things. They're not a very strong unit because everyone's individual. However, this is like the American team, the Chinese team, and the Australian team. There's like a big lattice of them, okay? They all count as one big unit. All right, so same, just like my analogy of the medal tally thing, same thing here, guys. Lattice being a big unit, do you need a lot of energy to overcome or very little energy to overcome an entire lattice? Lot of energy to overcome a lattice. What about to overcome discrete molecules? Do you think a lot of energy or not so much if it's just a few individual molecules? Not so much. So I want everyone to know this statement. All right, I want everyone to be able to understand this statement is that a large amount of energy is needed to overcome the metallic bonds in a metallic lattice. A large amount of energy is needed to overcome the metallic bonds in a metallic lattice. Therefore, a large amount of energy is needed to overcome the metallic bonds in a metallic lattice. You need the hand to write. Michael, can you tell him to write? Because I don't think he gets it. Yes, with the hand. All right, good. All right. Therefore, metallic substances have high melting points. And do you know what I'm going to write next lesson? What I'm going to write next lesson is this. I'm going to write down a large amount of energy is needed to overcome ionic bonds in an ionic lattice. That's what I'm going to write down next lesson. Large amount of energy is needed to overcome ionic bonds in an ionic lattice. And because of that, guys, guess what type of substances have high melting points? Ionic substances. What I'm going to write 2 weeks after that is this. I'm going to write down a large amount of energy is needed to overcome covalent bonds. A large amount of energy is needed to overcome covalent bonds in a covalent network lattice. In a covalent network lattice. And because of that, what type of substances have high melting points? Covalent network substances have high melting points. So in summary, guys, what type of substances have high melting points? Anything that exists as a lattice. Covalent network substances have a high melting point. That's what these three guys have in common. That's what metallic substances, ionic substances, and covalent network substances have in common. Because they exist as a lattice, they need a large amount of energy to overcome the bonding within them, and therefore they have high melting points. Guess which one doesn't need a high amount of energy then? Covalent, molecular substances. So when I discuss that in week 3, you'll notice I'll say not so much energy needed to overcome the bonding between them, and therefore not high melting point, boiling points. Okay. All right. So in summary, why do they have high melting points, guys? What's a quick summary of all of this? I know I've written all these words, but what's a quick summary? I just wrote it just then. What did I write down? A large amount. You need to be able to regurgitate this sentence. A large amount of energy needed to overcome the metallic bonds in a metallic lattice. And if you need a lot of energy to overcome the bonds in a lattice structure, expect the melting point, boiling point to be high. Expect the melting point, boiling point to be high if it's a lattice. All right. And that's a very, very important property. All right. And guys, not so important. They are, in fact, I don't like this word. Can everyone get rid of this word? It's not meant to say hard. They are strong, but soft. Strong, but soft. Does anyone have another word for soft in terms of metals? Ductile and malleable. Isn't that what ductile and malleable is? Something that can be bent easily, something that can be rolled up into wires. It's strong, but it's soft. You can bend it still, okay, and change its shape. So it's not exactly hard. All right, I'm not too interested in that property. What are the main 4 properties I'm interested in? High electrical conductivity because of the charged mobile particles. Good. Not interested in that. Malleable and ductile. And malleable and ductile has very specific words you have to use. When sufficient force is applied, layers of positive ions are forced to move relative to one another. However, the delocalized electrons are free to move into the regions between the ions, and therefore the metallic bonds remain maximized. The metallic bonds are still maximized. And because metallic bonding is non-directional, you have to regurgitate that, like exact sentence, exact paragraph. All right, why are they shiny, guys? The interaction between the photons of light and mobile electrons is what creates the shiny appearance. Don't have to say much more. And why do they have high melting points? You write that large amount of energy needed to overcome them. Okay, those are its main properties, and that's what you write. All right, so what we can do is do some of the questions. Let's go question 1. What exactly is metallic bonding? Metallic bonding is the electrostatic attraction between, guys, what was it, the attraction between? And now I hope you guys remember electrostatic means positive, negative, okay? So it's the electrostatic attraction between what two things? Between the metal cations, which are positively charged, and the C of, yep, valence. One more word, delocalized, valence, electrons, whichever negative charge. That is the definition of metallic bonding itself. It's the attraction between the metal cations, which are positively charged, and the C of delocalized valence electrons, which are negatively charged. That's it. For an element to be a metal, what's the major characteristic of the valence electrons? What do the valence electrons have to be? Delocalized. It's in the sentence. Delocalized valence electrons have to be localized. The valence electrons have to be delocalized. If you want, you can write down that the element must be ionized. I'm just going to write that they have to be delocalized. All right. Viva, you want to give me, sorry, Nearby, you want to give me 4 good properties of a metal? All right, ductile / malleable, and give me another word for ductile / malleable. Metals are what? Everyone else in the class, I said it 2 minutes ago, they are soft. All right, soft but yet strong. All right, what's another property? Lustrous, yes. Good. Good. So electrical conductors, yes. Good. Those are the 4 main ones. You have other ones, high thermal conductivity and blah, blah, blah. High melting point. And guys, what else do they want you to do? But I just can't be bothered doing it again. You have to explain them. All right. I just explained why it had every single one of them. Let's do it verbally at least. Verbally, guys, why are they ductile and malleable? You know, I might as well do it because question 5 says define ductility and malleability. What does ductility mean? Can be bent easily into sheets. That's what ductility means. And what does malleability mean? It can be drawn into wires. Sometimes I hear some teachers say the word rolled into wires. Same thing, okay? Yes, it's the other way. Sorry, my bad. That's my fault. Ductility means it can be drawn into wires, and malleability means it can be bent easily into sheets and bent and whatever. Molded, basically. All right. And guys, why are they, what allows metals to do that? So what's the key? You need to regurgitate this sentence again and again and again. If sufficient force is applied, to a metal, what layers slide? The metal cation slide, yes, the metal cation layers slide. That's the first thing that happens. Are those electrons going to be sad, like, oh shit, we lost our companion? No, what are those electrons free to do? We can explain the C of delocalized valence electrons are free to fill the gaps between the metal cations. They are free to fill the gaps. They're free to move and fill the gaps. They're free to move and fill the gaps between the metal cations. All right. So if sufficient force is applied, metal cation layers slide, but the sea of delocalized valence electrons are free to fill the gap. So then what we can explain is that as metallic bonding is non-directional, as metallic bonding is non-directional, what does that mean? The metallic bonds remain, metallic bonding remains maximized, and the metallic structure remains. When you bend a metal, it doesn't snap. It still remains metal because we're still just keeping it together. You need to be able to write those 3 words, sentences, to explain explicitly why metals are malleable and ductile. All 3 sentences. 1 to show that the metal cation layers are sliding. 1 to say that sea of delocalized valence electrons will just fill the new gap that's been formed. And Lucky Last saying that because they fill the new gap, and because their bonding is non-directional, because they're not loyal to any particular cation, we maximize the metallic bond still, and the metal just remains, its integrity remains. We're all happy with that statement? All right, cool. All right, that explains why they're malleable and ductile. Can you guys verbally explain to me why they're lustrous? The interaction between the what? Photons of light and the sea of delocalized valence electrons makes them shiny. It's not even really an explanation, but it gets you the marks. Interaction between the photons and the sea of delocalized valence electrons. Can someone explain to me why they're good electrical conductors? What do you need for electrical conductivity? Charged mobile particles. So the sea of delocalized valence electrons, the sea of delocalized valence electrons are charged mobile particles. They are charged mobile particles that conduct or carry current, whatever you want to write down. That carry the current. You had to explain to me that we have mobility and we have charge. That's the 2 things you need, mobility and charge. So they are able to carry the current. All right, and the 3rd time I'm writing this today, why do they have a high melting point? Large amount of energy needed to overcome what? Metallic bonds in a what? In a metallic lattice. See how predictable this topic is? All right, it's super easy. All right. So guys, metals bend relatively easily, right? That's why if you have like pure gold, it's not very hard. It bends easily. So what if you want to like, does that mean that like this drink bottle, I don't want it to bend easily? All right, so we don't usually use metals in their pure form. How do they use them? Alloys. Everyone knows that we mix stuff together. Usually we have alloy. Yes, we don't use pure iron. We use like stainless steel. It's a bit stronger. You don't, if you buy jewelry, apparently you don't buy like 24 karat gold. It bends a bit easily. You buy like 22 or 20. Especially, I've learned this since getting married. If you're going to put a diamond in the gold needs to be strong and not bend. So you can't, the Indian salesman's like, no, 18 karat if you want diamonds. Okay, so you need the gold to be a bit less purity so that it can be stronger to grip the diamond. Otherwise, it's too soft and it bends and blah, 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 pops out. All right. Are we all happy with that concept? All right. So I want to explain to you why exactly, I want to be able to explain to you why exactly alloys are stronger. All right. What makes an alloy stronger than the normal substance? All right. And to really explain it to you guys, does an alloy mean you put something else into it? All right. To really emphasize the point, I'm going to make it like this big. Let's pretend I put a atom, which is really, really big. All right. I'm really trying to emphasize my point. Now, obviously, guys, they do have an atom of a different size, but I'm really trying to emphasize my point. All right. Michael, Shh. Everyone listen to Michael. Michael, is it going to be, forget the red for a second. So just look at like this region right here. Is it easy for these layers to slide against each other? Yes. Does everyone agree they're all the same size? They all just roll relatively easy. What if I chuck this big thing in the middle? Do these layers slide as easily against each other? No, it's of a different size. Now these layers, they're like, oh, which way do you want me to go? I can't go anywhere. This sounds like, which way do you want me to go? The layers don't slide as easily because you've got an impurity atom of a different size. Does that make sense to everyone? You put something of a different size in there. So what's the exact phrase that I've used? The exact phrase that I've used is, when mixing a metal with other metals and non-metals, the properties can be altered to make it used for a particular use. Pure iron is soft and bends easily. However, if you put carbon in it, so hypothetically, guys, let's pretend this is carbon. This is carbon, and I'm putting carbon inside. I'm putting carbon inside my this is carbon, and I'm putting carbon inside my iron. This otherwise was just normal iron. This was normal iron. This was iron. However, I'm putting carbon inside it. All righty. And guys, what I want everyone to understand is the atoms of impurity. What's the exact phrase that we need to understand? Disrupt the orderly nature of the lattice. It's not of the same size. It disrupts the nice orderly arrangement that it had and makes it more difficult for the layers to slide over one another. What's another way of saying that the layers don't slide over one another easily? What's another way of saying that? The metal has become what? Harder. Everyone agree? Now it makes the metal harder. Alloys therefore tend to be harder and stronger. So now you guys understand how alloys work. Everyone happy with that? You understand how alloys work. You put an atom of a different size, we call it an impurity atom, and it makes the layers more hard to slide. And guys, if you read the question, I didn't get up to it. It says, explain why an alloy is much less malleable than pure iron. Okay, and we just did the discussion for it. Not too bad. Are we all happy with that? So now you understand what type of substance as well, metallic bonding, and you understand why it has those properties. Okay, cool. Well done.